videos for target 5, graphing logarithmic functions. With and without technology, well, we're really not going to do anything with it since some of your calculators won't be able to graph these. They don't have the appropriate function, TI-83s and so forth. So I'm going to teach it so that you don't need the calculator. We might do a little bit with the calculator in class, though. You'll need to have watched target 3 videos for sure, and then target 4 is recommended, but you could do without it if you haven't watched it yet, because we're going to use what we learned about inverses in target 4. Exponentials and logarithms are inverses to perform the graph to graph a logarithm. So with that said, in order to graph log base 3 of x, we need to have graphed y equals 3 to the x. So we have those points. I copied everything that we did in target 3 for number 1. We have the table, we have the picture, we have everything over here to the right that we can reference. And simply put, if you're going to put in a value for the exponent, like 3 to the negative 4, and get out 1 over 81, as the table suggests, then when you put in log base 3, when you put the output 1 over 81 into that, the input negative 4 comes out. Meaning, if you put in an x 1 over 81, you get an output of y value negative 4. They switch x and y. If, we'll do one more, log base 3 of, we'll do 4. We'll do the one at the very bottom. If you put log base 3 of 81, so if you put in 81 in log, you get out of 4. And I know this because I'm looking down here at what you get when you put 3 to the 4th. When you put 4 into the exponential, you get 81 out. So switch your x and y. The output 81 becomes the input of log. The input of the exponential becomes the output of the log. So that turns into the point 81, 4. And then you can almost fill in the in-between just by copying and transferring the points over from the table to switch your x and y. So 1 over 27, 1 over 9, 1 over 3, 1, 3, 9, 27. So when we go to graph this logarithm, we're probably going to need to count by something different on the x-axis instead of the y-axis. Previously, we changed the y scale to 3. Now we'll change the x scale to 3. So I'll get rid of that old version there. So counting by x scale, counting by 3. First point I'd graph is 3, 1. Write 1 up 1. Then 9, 2. So write 3, 6, 9 up 2. Write 27 up 3. So 3, 6, 9, 12, 15, 18, 21. 24 gets us to the edge of the graph. So 27, 3 would be kind of right there. All right, now going backwards because I can't fit 81, 4. Going backwards, graph 1, 0. This is where it gets a little tricky. When you're counting by 3s on the x-axis, 1, 0 is about 1/3 of the way over. 1/3, negative 1. Right a little, down 1. You know what? I really shouldn't have deleted that. Sorry to interrupt the train, or interrupt the thought process right there. Let me bring that image of our old picture back over here. There we go. We'll still want that. Graphing 1/9, negative 2 would be right a little, down 2. Graphing 1 over 27, right a little, down 3. 1 over 81, right a little, and down 4. So that trend where we had decimals getting closer and closer to 0 is there on the logarithm, except they're getting closer and closer to 0, getting closer and closer to x equals 0, getting closer and closer to the y-axis. So connecting all the dots in between to illustrate the points that we could have found if we had the calculator to do so. All right, so there's logarithm. And you can almost see if you drew a dotted line at y equals x. It's hard to draw that freehand here. If you flipped that over the dotted line, you'd get the picture over here that we created with y equals 3 to the x, because they're inverses. They should be symmetrical about the line y equals x. But anyways, moving on, that's neither here nor there, just a visual confirmation that we're getting the correct picture. Y-intercept, where does that cross the y-axis? And because these fractions over here get closer and closer to 0 but never get there, there is none. And that's going to affect your domain because all of the points that we can actually plug into this problem begin at, well, not 0, but bigger than 0. Your domain is x is bigger than 0. Every point that we graph is to the right of the y-axis. So x's are bigger than 0. Furthermore, if you remember your inverse relationship, domain and range switch, which that kind of confirms that, all right? And then the range, that function we just graphed, goes down forever and it goes up forever slowly, so the range is all real numbers. And then again, you can compare your previous domain to the range, and they kind of switched domain and range. That's pretty typical of inverses. Every now and then it won't be, but pretty typical of inverses. I'm referencing square root of x plus 2 in your homework for target 2 and how when you find the inverse it's a quadratic and the domain and range of your original doesn't really match that. That probably shouldn't be in this video, but I couldn't help but explain what I meant by that. But that concludes graphing log base 3 of x. When we go to graph our next one, graphing log base 1/4 of x, we are going to need y equals 1/4 x already graphed. So just to remind you, let's see where, there we go. We did this in the Learning Target 3 video, and I'm just going to take all of those points from the table and switch them, and that will help us. That'll allow us to graph the logarithm with base 1/4 because those are the inverse. The logarithm is the inverse of exponential. So just going to take those and transfer them over. So we had -4 and 256, then -3, -2, -1. Oh, sorry, I meant to switch those. Sorry about that. -4, -3, -2, -1, 0, 1, 2, 3, 4, and that one was 256. And then again, going back to the picture, that was 64, then 16, 64, then 16, then 4, then 1, then a 4th, then a 16th, then a 64th, then a 1 over 256. All right, so first step to graph a log, graph the exponential. Now switch x and y. I'm going to count by 4s on the x-axis, so graphing 4, -1, right 4, down 1. Graphing 16, -2, right 4, 8, 12, 16, down 2. Graphing 64, -3, it's not going to fit, but it's going to be over in this ballpark, so something like that. Graphing 1, 0 would be right a quarter, right a fourth when you're counting by 4s, up 0. Right a fourth, up 1, right a little, up 1. Right, let's see, 1/16, comma 2, right a little, up 2. 1 over 64, right a little, up 3, and so forth and so forth. So our logarithm gets closer and closer to 0 on the fractions here, but it will never get there. Therefore, the domain is still greater than 0. And the range, it goes up and down forever, so all real numbers. And again, there is no y-intercept. So I don't want you to start thinking the domain and range is always greater than 0 for the domain and all real numbers for range, because it can change. Now, granted, the range will never change, but the domain can change. And we're going to explore that in the next two. So we'll explore what happens when you add 1 to the output. Again, refer to video 3 because we've already done this before. And we're going to take a look at, we did it with exponentials then, but now we're doing it with logs. We're going to explore what happens when you subtract 2 to the input. How does that affect the picture? So both of these reference number 1, log base 3. All right, so to illustrate how you handle number 3, we'll take a look at log base 3 of 81. Because when you put in 81 into the log, according to what we did in number 1, it comes back as 4. So that turns into 4. But then our function we're graphing here in number 3 says, all right, now add 1. So 4 plus 1 turns into 5. Meaning, if you put in an 81, you will get a 5 as your output. Now let's do that manually one more time. Let's do that manually one more time. Input. If you input 27, so log base 3 of 27, you get a 3. But then your function we're graphing here says add 1, so we get 4 as our ultimate output. So input was 27, and the output was 4. Now I think you can already start to see the pattern. Your inputs are the same. 81, 27, 9, 3, 1, 1/3, 1/9, 1 over 27, 1 over 81. But your outputs are being moved. They're changing. So 81.4, 81.5. How are they changing? 81.4 shifted. It moved to 81.5. It moved up 1. So if you add 1 to your output, you're moving your y values up 1. So you can just continue to add 1 to your outputs. So 2 plus 1, 3. 1 plus 1, 2, and so forth. All right, we're not going to graph this one, saving time on the video. Just going to point out that your x values are getting closer and closer to the decimal 0. Your y values have shifted up 1. So your domain is still greater than 0. They're getting closer and closer to 0, but we'll never get there. And your range has went from all real numbers to all real numbers plus 1. And again, when you add 1 to infinity, you still get infinity. So it's still all real numbers. All right, number 4. What happens in this one? Our domain or range 1 is going to be affected. Let's see. All right, to illustrate what happens in number 4, let's consider log base 3 of x minus 2 of box minus 2. And how are we going to make that turn into, we'll go back to our first one, how are we going to turn that into 256? Because if we can put 256 into the logarithm, we know that negative 4 comes out. Well, if you're going to get 256 in this situation after subtracting 2, you're going to have to put in 258 right there. Because 258 minus 2 turns into 256. And log base 3 of 256 is, according to our work in number 2 up above, it turns into negative 4. So the moral of that story is if you put a 258 in your input, out comes a negative 4. All right, let's do one more of those by hand. Log base 3 of blank minus 2. All right, the next one I know is 64. Log base 3 of 64. I know that answer. That answer is negative 3, according to the table above. So what is it that we would put in that box to make that turn into 64? We put 66 there. So input is 66, and effectively you get log base 3 of 64, which turns into negative 3. All right, now let's pause and take a look at what's happening here. How are our points shifting, or what's changing about those values? Well, our y values are not changing at all, and our x values are going up 2. Our x values are getting bigger by 2. That's a movement of right 2. When you subtract 2 to the input, you move your points right 2. So I'm going to just continue moving my points, my x values, right 2. So the 16 moves to 18. The 4 moves to 6. The 1 moves to 3. And then adding 2, adding 2, adding 2. I get the decimals 2.25. I get 2. Let's see, I just did this a second ago. We'll do it with the calculator, not on screen, because it's easier to do them not on screen. When you add 2 to a 16th, you get 2.0625. And when you add 2 to a 64th, you get 2.0156, so 2.016. I'll round that there with 3 decimals. And then when you add it to 1 over 256, you get 2.0039, so 2.004 about. And your output's negative 2, negative 1, 0, 1, 2, 3, 4. All right, I'll graph this one again because I want you to see the change in domain that's about to happen. When you graph, let's see, counting by 4s again, like I did in number 2, counting by 4s on the x-axis, I'll start with 3, 0. Right 3, up 9. That'd be about right there. 6, negative 1. Right 4, and right 2 more, so it'll be about right there. Down 1. Right 18, so 4, 8, 12, 16, 17, 18, and then down 2, right there. 66, negative 3, that'd be right 4, 8, 12, 16, 20, 24, 28, 32. That'd be about over here in that vicinity. So something like that. Here's where we change our domain. When we graph our next points, 2.25, that'd be right about 2.25 up 1. Right 2.06 up 2. Right 2.01 up 3. Right 2.004 up 4. And you get the picture. The decimals are going to keep getting closer and closer and closer to what? Closer and closer and closer to 2. Not 1, but 2. So all of our points on this picture start to the right of x equals 2. So your domain is x is greater than 2. Meaning, when you subtract 2 to the input, you move your domain right 2. You move your input right 2. There is no y-intercept, and the range goes up forever, down forever, so still all real numbers. Again, this last part, like video 3, is a little bit more for your pre-calc and calculus bound students. These are illustrating vertical asymptotes, like x equals 2. In the last one, the one we just finished, if you drew a vertical line at x equals 2, I'll do the best I can to draw that. X equals 2. That's not bad. I'll take that. All of your points are getting closer and closer to x equals 2 as you move up on that picture, as you move left. But they'll never get there. That's called a vertical asymptote. There was an x equals 0 vertical asymptote in question number 2 and question number 3, vertical asymptote at x equals 0, also known as the y-axis. Something that you'll use a little bit more in depth in calculus and future math. But that is target 5 in about 17 minutes.